let's come to section 5, norms of vectors and matrices. In this section, I will teach you a mathematical conception, norms. Okay, what does it mean? Okay, in first chapter, we discussed the error for number, remember? Okay, x is a exact value, a number, right? And we use a approximate value to approximate x, right? So we need to consider the error x minus a. Okay, so in the here you see in the figure, this is x and this is a, right? And we can consider the absolute value of the absolute error. So it means the distance between x and a, the 2 points on the x, right? Okay, now in chapter 2, we consider to solve linear system ax equal to b. Okay, now we know we can use Gaussian elimination, LU factorization to solve the linear system. Of course, usually we cannot obtain exact vector. Now I use arrow to represent vector, right? That means we also can obtain execute the arrow with arrow the vector. Okay, so the problem like here, how to estimate the error between the two vectors? Now for numbers x and a, we can just use the absolute value to represent the distance between the two numbers. But here, x is a vector like this, right? This is x, and x tutor may be like this. This is x tutor. So now we need to estimate the error between the two vectors. Of course, we can consider the subtraction, the difference, right? So x error, the vector minus x tilde error. Okay, the two vectors. But now we know the difference is also a vector, right? Okay, for example, if x has n-dimensional vector, so x1, x2 to xn, and x tilde, x1 tilde, x2 tilde to xn tilde. Okay, so in this case, E is also an n-dimensional vector, right? So it is E1, E2 to En, right? Okay, we need to estimate the error. Usually it's better to just use a number to estimate the error, right? And also if we obtain another vector, for example, like this, I denote this vector by y. Okay, so how to compare? If we use, also we can use y vector to approximate x vector. Which one is better? X tilde or y? Of course, we can also consider the difference between x and y, right? So, for example, I write here another vector, for example, denoted by epsilon, okay? Epsilon is also a vector by x vector minus y vector. So it is x1, x2 to xn minus y1, y2 to yn, right? Okay, so then we know this arrow vector is x1 minus y1, x2 minus y2, xn minus yn, right? Now you see, we have two approximate vectors, x tilde and y, and now we need to compare which one is better, right? So that means we need to compare the two vectors E and epsilon. Okay, so in order to compare or estimate the error vector, now we need to generalize. We need to generalize the absolute value for numbers to the norms. It's okay for you? So firstly, you need to understand what's the meaning of norms. Norm means generation of distance, okay, or the length. Because now you see the absolute value of x minus a means the distance between x and a. They are two numbers, or represent the length of x minus a, right? Okay, here now you see this is x vector, this is x tilde vector. So the difference like this. This vector is okay for you? This vector, now you see this vector is x minus x tilde. It's okay for you? This vector is arrow vector. And also we have another one. If I move, okay, I write here, this is x. Then this vector, now you see, this is x minus y. Okay, now we need to compare the two arrows, the two vectors, right? It's okay for you? So that means we cannot compare vectors directly. We can only compare numbers. You should understand, right? It's okay for you? Why we cannot compare vectors? Here, this is a unit circle, right? Unit circle. This arrow, this arrow, this arrow, this arrow. Because, okay, here, this is a unit circle. So that means the length of these four vectors, they are same with same length. They are different by the directions, different directions. So we cannot compare. We can only compare the length, right? So we can only compare the length or the distance, right? Okay, now you see. Now we use norms to generalize the length or distance for vectors or points. That's okay for you? So you should understand the topic of this section. In order to compare the error for vectors, also we can compare the errors between matrices. Okay, in some, for example, A is an n by n matrix. Okay, this is exact matrix. And also we can consider its approximation. For example, B, another matrix. Okay, we use B to approximate A. Now we need to compare, we need to estimate the error, right? Now you see, the error is also a matrix. So how to estimate? Or another one use C, another matrix, to approximate A. Okay, now we also have the arrow matrix, A minus C. This arrow is A minus B. Which one is better? B or C is better, right? So in this case, we need to consider the distance between two matrices. Okay, so we generalize by the norms. It's okay for you? Okay, so let's start from vector, the case of vectors, the norms of vectors. Okay, or vector norms. Let Rn denote the set of all n-dimensional column vectors with real number components. Okay, that means, for example, we denote x vector by x1, x2 to xn. It is a n-dimensional column vector, right? So real vector, real numbers. So that means each component xi is a real number. I use this r, okay? Means real number. So because this vector is n-dimensional vector, so x belongs to Rn, okay? here I use arrow to represent the vector. Xi means just the number component. Okay? Now, we need to define a distance in Rn, the space. Okay? We use the notion of a norm, which is a generalization of the absolute value on R, one-dimensional real numbers, right? Okay, the set of real numbers. Okay, we can use the X to represent all the real numbers. It's okay? Now, here is the orange point. Okay, this is X. Okay, this is Y. So, the distance between the 2 points on the one-dimensional real axis, right? So, we use absolute value of X minus Y to represent the distance, right? The distance. Okay, now, we have an n-dimensional vector X, and also we have Y vector Y. It is also Y1, Y2 to Yn, right? N-dimensional vector. So, we need to define the distance between the two vectors. Also, we can consider the distance for X and Y, respectively. It's okay for you? So, now we need the conception of norm. Okay, now here, we use absolute value because X and Y, they are two real numbers. Okay, so we can put them on the real X. Okay, we use absolute value of X minus Y to define the distance between two numbers X and Y in one-dimensional real X, R. Okay? Okay, now let's show you the definition of vector. The norm, vector norm, okay? A vector norm on Rn, n-dimensional space, is a function. Okay, so firstly, you should understand norm. Norm is a function defined on the n-dimensional space. Okay, now you see the symbol. We just use double line. Okay, so it is similar to absolute value. Okay? So if X just a real number, it is a real number, then we can define, we use, okay, the two lines to represent the absolute value of X. Now, we use double line. Okay, this dot means the vibro, okay? Okay, so that means if now X is an n-dimensional vector, then we use double line X vector, okay? Vector, okay, this symbol, to define the vector norm. Okay, so firstly, it is a function, but this function is special, okay? From Rn to R. That means we just use a number to define the norm, okay, with the following properties. The first property, okay, for all n-dimensional vector here, because here we use X directly to reference a vector. Okay, so you should know this X is a vector, not a number. Okay, vector. Then its norm is positive. It's usual condition because we know distance is positive, right? So of course norm should be positive, bigger than or equal to 0. Okay, second. The norm of X is 0 if and only if X is 0. Because we know here, just like you can compare the definition of norm with the absolute value, right? Okay, for absolute value, X bigger than or equal to 0. It's okay? Absolute value is positive. And second, we know absolute value is 0 if and only if x is just 0. In this, here, x is a number. It's okay for you, but here, x means the vector. Okay, so now you see this property, just like absolute value. So, norm is generalization of absolute value. It's okay? Absolute value is also a function. Also function, right? It's okay for you? The figure, the function like this. Absolute value. It's okay? It's okay? Like this. Okay. Third, if you use a number, a real number alpha, multiply the vector x, then it is a new vector, right? Okay, the norm or the length of alpha x is equal to alpha absolute value multiply the length or the norm of x, the vector. Okay, for any real number alpha and any real vector x. It's okay for you? Okay, you should know, actually, you use alpha multiply the vector, you don't change the direction. It's okay for you? If this is vector x, here is O, the original point. Okay, for example, 2x, then you don't change the arrow, the direction, right? Here, 2x. I use arrow here to represent the vector. So that means the length is twice. It's okay? And if you consider minus x, it means, okay, multiply minus 1. Okay, because minus 1 is negative, so that means the direction, okay, you need to rotate the pi 180 degree, okay, or reverse, anti direction, minus x. Is okay? Okay, but the length, if you consider the length of the vector, then just multiply absolute value of alpha. It's okay for you? Okay, so this is the third property for the norm. Okay, the fourth. The norm of x plus y should be less than or equal to the norm of x plus the norm of y for all vectors x and y. It's okay for you? Actually, this is a triangular rule. Okay, actually this is a triangular rule. Okay, I need to clean. Also, actually we can compare with absolute value just like this. Okay, now you see alpha multiply x absolute value equal to, we know alpha absolute value multiply x absolute value. It's okay? And for here, if we have two numbers x and y, then x plus y absolute value less than absolute value x plus y absolute value. It's okay? So now you see the four properties also are satisfied for absolute value, right? Here we generalize the absolute value to norm from number to vector. So we use double line to represent norm. Okay? You can consider norm as length. Okay? Length of the vector. Okay, so here it is just the triangular rule. Now you see this is vector x, this is vector y, and we know this is vector x plus y. It's okay for you? And we can move y to here. So this vector also y, right? So this is x and this is y. It's okay for you? Then from here to here, this vector is x plus y. Okay, we know the length. This is a triangular. Okay, triangle. So the length of this edge, okay, should be less than the length of y and the length of x. the summation, right? So here, triangular rule. It's okay for you? So that means, okay, we generalize the absolute value or to the norm, vector norm. It is a function and satisfy the four properties. Okay, positive. Okay, and if the norm is 0, if and only if x is 0, and multiplication with number, then we can move alpha. We can move alpha outside the norm here with absolute value outside, right? Outside the norm, then by absolute value and the triangular rule. It's okay. You can compare the four properties with absolute value. So, especially if you just consider one-dimensional vector, then norm is just absolute value. In the case of just consider one-dimensional vector, right? One-dimensional vector, just a number. It's okay? And then we can use the norm of x minus y to define the distance between two vectors x and y in the Rn, the n-dimensional space. It's okay for you? Okay, now you see, actually, here is the original point. Then this vector is denoted by x, and this vector is y, Then we can see, okay, now you see the difference between x and y. Okay, this vector represents the difference between x and y. Then we can use the norm. We can use the norm of x minus y to define the distance between the two vectors x and y. It's okay for you? And also we can use the norm of x. Now you see, the norm of x, the vector norm, to represent the distance between the point here to the original point. It's okay for you? Because x norm equal to x minus O norm, right? Okay, so this means the distance between the point x to the original point. It's okay for you? So that means norm defines the length. Okay? So that is why we need a vector norm. Now we can just use a number to represent the norm, right? Actually, in fact, you already used the norm. You just don't know the name. Actually, you used, for example, okay, if we need to compare the score for different students. For example, we have 3 students, okay, X, Y, and Z. Okay, we have 3 students. Okay, now we need to compare which student is best, and of course we have different subjects. For example, okay, for X, the student X, we have 3 courses. For example, we have 3 courses. Okay, for X, he obtained 3 scores. Okay, for example, 90, 80, 90. For 3 subjects or 3 courses. Okay, and for Y, this is X, and for Y also, student Y also obtained his scores. Okay, for example, 100, 60, and 100. Okay, change. Okay, for example, 70. Okay, another one, Z, For example, okay, 60, okay, 180. Now, you need to consider, okay, which one is the best student. You can use different rule, right? You can use different rule. Okay, for example, we can consider the total scores. Okay, that means, okay, we just consider the summation between the two elements, components. Okay, so by total score, we know X, the total score is 260. It's okay? 260 for total score for X. And for Y, the total score is just 230. It's okay? And for Z, its total score is also 240. Now you see, by the total score, you only need to compare the three numbers. Which one is biggest number? Of course, 260, right? So by the total score, we know X is the best student. It's okay? Actually, you see, you define a function by total score. So total score is a vector norm for the three vectors. Now you see X, X1, X2, X3, Y, Y1, Y2, Y3, Z, Z1, Z2, Z3. There are three vectors. Okay, we can use total score to compare the length of the three vectors. Okay, of course you can change rule, which maybe another teacher said, okay, we don't compare by total score. We just choose the best score. Okay, now that means we need to use maximum components for each vector. Then now you see, for X, if you don't use total score, you use best score. Now for X, its best score is 90, right? Okay, now we change. I write here 90. And for Y, okay, first score, it is 100. Okay, so it is 100. And for Z, also here, the best score is 100. Now, in this case, the student X is not the best one. It's okay for you? Now, actually, you use different function, different rule. Okay, that means you can define different different vector norm. So that means norm is not unique, right? You can choose different norm. Okay, so the definition for norm, it is a function, but it needed satisfy the four properties. It's okay for you? Of course, I will introduce you. Total score, best score, there are two kinds of vector norms. I will introduce you later, okay, by mathematical definition. But here you should understand, actually, norm is just a new name for you, but you already used the idea of norm before, okay? Okay, now let's consider the general case, n-dimensional vector, right? So x1, x2 to xn, they are n components, real numbers, right? For any real vector, okay, now here, the t, subscript t means the transpose, because I write it in the raw vector, but we define by column vector, right? Okay, now you see, firstly, I introduce you the name L1 norm. Now you see how to obtain the L1 norm. I use 1 here, subscript to represent the rule. That means we choose L1 norm by the definition, just the total score. Now you see the summation of xi absolute value. But you should know here we need to use the absolute value of xi, the summation I from 1 to n. Of course, in the example here, because usually because I use the example, the score, we don't have negative score, right? Always use positive. So here I don't see by absolute value, but for general case, because for general case xi, they are real number, maybe positive or maybe negative. So here we need to use absolute value for each xi, because you should know, we know the norm should be positive. It's okay? So that is why here we need to use absolute value for each xi. It's okay for you? So here I give you the mathematical name by L1 norm. Actually, you can call it by total score. It's okay? Just like total score. Okay, the second norm. Okay, L2 norm. L2 norm, here I use 2 to represent this kind of norm. It's just the square root. Now you see square root of the summation of xi absolute value square. Actually, this is just the Euclid norm. Okay, so for example, we know this point, for example, for example, here 3, 2. That means x is a 3, 2, two-dimensional vector. Okay, this vector. So we know this point, the distance of the vector by square root of 3 square plus 2 square equal to square root of 9 plus 4. So it is 13. It's okay for you? Now you know this norm before. Okay, we use another name is Euclid norm, or Euclid distance between the two, the original point to this point 3, 2. It's okay for you? So it is square root here, square root, or you can just write square root x1 square plus x2 square plus 2xn square, right? This is a square root. And also we can use like x transpose in the product with x. It's okay? It means x transpose means the raw vector x1 to xn in the product. Here means in the product, right? In the product with x1 to xn. It's okay for you? You should know the inner product, right? Okay? Okay, so it is just x1 multiply x1, so x1 square plus x2 multiply x2 square, and plus last is x1, xn multiply xn, so xn square. And don't forget the square root. It's okay? Okay, the third kind of norm, L infinity norm. Okay, here we use infinity subscript to represent this norm by defined by maximum number of absolute value of xi, I from 1 to n. Okay, now you see this is the best score. It's okay for you? So L1 norm is the total score. L infinity norm is best score. I just take the example. It's okay for you? Of course, in general case, we can define LP norm. I think in some papers, okay, maybe in your research, you will use LP norm. So what it means LP norm? Just replace here 2 by p. Now you see 2 by p, and so here square root 1 over 2 by 1 over p, and here 2 by p. So you consider the xi absolute value, the power of p, consider the summation, and compute the root of 1 over p, power 1 over p. It's okay for you? That means when P is 2, actually, when P is 2, then LP norm come to L2 norm when P equal to 2. And also, when P equal to 1, actually, it is just the L1 norm. Why? Now you see, if here P is 1, just the absolute value. 1 over 1 is 1, so come to the total score. It's okay for you? So that means L1 norm and L2 norm are two special cases for LP norm. Of course, in mathematical analysis, we can prove when P goes to infinity, then LP norm goes to L infinity norm. Okay, now you don't need to master this result, but it's better for you to understand the relation between the four kinds of norms. Okay? Actually, for you only need to know how to compute the norms, especially for the three kinds of norms, because they are popular. Okay? Okay, especially the second one, L2 norm, it is just the Euclid norm. Okay? It's okay for you? Can you see? Euclid norm. Okay. Let's consider okay, for you, I show you example. Okay, now let's practice this example to help you to understand the norms. Okay, now we need to find L1 norm, L2 norm, and L infinity norm, the three norms for the vector x. Okay, it is a three-dimensional vector with three components, -1, 2, and 4. Here, T means a transpose. That means x is a Coulomb vector. It's okay for you? Okay, now let's practice. Okay, you should remember L1 norm means total score, but you should note the total score we need to compute the absolute value, then compute the summation. It's okay for you? So for x1, L1 norm for x, this vector, it should be -1 absolute value plus absolute value of 2, just 2, right? Plus absolute value of 4. So the total score, okay, the L1 norm is 7. Okay, don't make mistake. Okay, don't compute like 4 plus 2 minus 1. That's wrong. Okay, you should remember always with by absolute value. It's okay for you? So total score by absolute value. This is L1 norm. It's simple, right? Okay, let's consider L2 norm. L2 norm, okay, the formula is square root of summation, right? Square summation. So -1 absolute value square. Okay, in this case, okay, the absolute value of a square, the square of absolute value is same to the square directly, right? Okay, so in this case is 1, and plus the 2 square, so it is 4, plus 4 square, 16, right? Okay, so it is the square root of 21. It's okay? So Euclid norm, right? Now we call the name by L2 norm. Okay, for L infinity norm, that means the best score, right? The best score also you should note by absolute value. So absolute value of -1, so it is 1. Absolute value of 2, it is 2. Absolute value of 4, it is 4. So you need to choose the best score. Of course, it is 4, right? It is 4. Okay? So infinity norm. Are you okay? This is the 3 norms. Okay, in addition, now let's practice another vector by 5, 0, 0. 5, 0, 0. Okay, now you see also special vector. Now, now for L1 norm. For L1 norm, now you see the total score, right? Like this. So the total score, the summation of absolute value of 5 plus 0 plus 0. So it's just 5, right? It's okay. And for infinity norm, the best score, of course, it's just 5, right? Also, we can consider the 2 norm. Okay, it is the square root of 5 square plus z square plus 0 square, right? Then it's just 5, right? Now you see 5, 5, 5. Okay. Okay. Now you see. Let's compare y and x. Now you see, if we choose L1 norm, so by L1 norm, then we know 7 is bigger than 5. So in this case, the 1 norm, L1 norm of x bigger than the L1 norm of y. It's okay? But if you choose infinity norm, then here you see x infinity norm is 4. 4 is less than 5. So in this case, the infinity norm of x is less than the infinity norm of y. Now you see, you obtain different results. Okay? We don't make a mistake. We just choose different rule. Right? So you use different rule. You can, if you compare different vectors, you can use different rule, but maybe you will obtain different results. It's not wrong, right? Because it is not a contradiction. Because we just use different rule. It's okay? Just like the example by the 3 students. Now you see here, in the beginning, okay, we show the 3 students, X, Y, Z, right? By 3 courses. Okay, now we can compare, we want to choose the best student, right? Okay, we can use different rule. If you use total score, then X is best student, right? But if you choose best score and rule, then X is not the best student. It's okay for you? So you can use different norm. Of course, now I introduce you the 3 kinds of norms: L1 norm, L2 norm, and L infinity norm. Okay, we need to check by these 3 definitions, they satisfy these 4 properties. So we can show. Okay, for example, let's check. Okay, I need to clean the screen. Okay, let's check, for example, by the total score. Okay, for the vector x, okay, n-dimensional case, okay, then the total score or L1 norm is defined by x1 absolute value plus x2 absolute value plus dots plus 2 xn absolute value, right? L1 norm. So here I use 1 to represent the L1 norm. Let's check. Actually, this is a function. This is a function. Now you see, for given the n numbers, you can obtain the L1 norm, right? So it is a function. Okay, let's check first property, because absolute value. So the number total score is positive for any vector x, right? It's okay for you? So that is why we need here absolute value, right? For the first property. Okay, let's check the second one. If the norm is 0, if L1 norm is 0, that means the summation of the absolute values, the summation is 0. we know, okay, if and only if for each xi, they are zeros. That means x is 0 vector. It's okay for you? So, check, right? Okay, let's consider the third property. If we consider use alpha number alpha multiply x, okay, so by the definition, L1 norm, so we know it's just you use alpha to multiply each component. So that is alpha x1 absolute value plus alpha x2 absolute value plus dots plus 2 alpha xn absolute value, right? Okay, by the property of absolute value, then equal to alpha absolute value multiply x1 absolute value plus alpha absolute value multiply x2 absolute value plus dots plus 2 alpha absolute value multiply xn absolute value. Now you see common term, right? By the common term, we have alpha absolute value multiply the summation of x1 absolute value plus x2 absolute value plus 2 xn absolute value. Now you see, that means just the alpha absolute value multiply the L1 norm of x. It's okay for you? So we prove this function satisfies the third property, right? It's okay for you? Okay, let's check the last property, x plus y. Okay, now we need to suppose y, the vector by the y1, y2 to yn, the n components, right? So what is x plus y? So x plus y, the vector by the definition and one norm. So it is x1 plus y1, right? Absolute value plus x2 plus y2, absolute value plus 2 xn plus yn. It's okay for you? Because x plus y, the summation vector, I use column vector. So it is x1 plus y1, x2 plus y2, to xn plus yn. Clear? Vector, right? So by the L1 norm, total score. Okay, of course we know by the triangular rule of absolute value. Okay, x1 plus y1 absolute value less than x1 absolute value plus y1 absolute value, right? Okay, continue. x2 plus y2 absolute value less than x2 absolute value plus y2 absolute value. Okay, plus dots, plus 2. Okay, last term. xn plus yn absolute value less than xn y absolute value plus yn absolute value. It's okay? Now we can put the x term together. Then it is x1 absolute value plus x2 absolute value plus 2 xn absolute value, right? And y1 absolute value plus y2 plus 2 yn. It's okay? Now the first part is just the absolute the norm of x, right? The second part is the L1 norm for y. It's okay? So now you see the one norm of x plus y less than or equal to L1 norm of x plus L1 norm of y. It's okay? So we check L1 norm satisfy the 4 properties. It's okay? So we know it is a vector, right? By this definition. Okay? And also we can check the maximum, the infinity norm. Okay, of course we also can check. Now, for example, the first property, positive, the maximum value, of course, should be positive, right? And the norm is 0. The maximum of absolute value is 0. That means all the components are zeros. Right? It's okay? And multiply alpha. So, if you multiply alpha, that means here, you use alpha multiply each component. So you can take alpha as a common term. Okay, by absolute value. So